Good morning or good afternoon. My name is Pedro Andrade. I'm from University of Madeira and I'm one of the authors of the paper entitled Improvement of Staircases Vibration Serviceability to Human Ergonomics, a case study. The other authors are Santos and Maia, both from University of Madeira as well, and also researchers at the Institute of R&D in Structures and Construction from the Faculty of Engineering of the University of Porto. So let's begin our presentation. The abstract of this presentation is divided in the following subsections: introduction, objectives and methodology, case study, experimental measurements, numerical model, improvement measures, results and conclusions. Contemporary slender and lightweight monumental staircases are becoming major architectural features of many buildings, hotels, museums and other public areas. Here are some examples of this type of structures around the world. However, design requirements of these are usually very aggressive, with long unsupported spans being standard, often resulting in low frequency staircases that are highly susceptible to human-induced vibration. In the traditional design, this type of structures normally were designed with only static loads in mind, but when assessing vibrations, only considering static loads can be a mistake, often resulting in a poor dynamic behavior. Moreover, in extreme cases, when pedestrian step frequencies match the staircase fundamental frequency or is one of its submultiples, resonance effects can and probably will occur, causing the feeling that the structure is not safe. The objective of this work is to propose different improvement measures to reduce the human-induced vibrations in a steel staircase with a well-known level of liveliness. Within this purpose, the following methodology was employed. Experimentally measure the vibrations of the sample steel staircase, build a realistic and precise F&A or finite element model of the steel staircase using the software SAP 2000, calibrate the finite element model built so that the vibrations numerically calculated be close to those experimentally measured, propose various improvement measures and recalculate the accelerations for each of the developed solutions. Compare the vibrations numerically obtained for each improvement measure between them and with experimental data. Finally, compare the vibrations verified after each improvement measure with the design guide SCIP 354. Our case study is a steel staircase located inside a building in Funchal, Madeira, Portugal, with surface connection between its 3 floors. You can see a drawing of the staircase in the left figure, which demonstrates the connection between all the 3 floors. In the right pictures is represented the real staircase, the structure of the real staircase. The sample staircase is known for its serious vibration problems, causing discomfort and being the object of several adverse comments by its users. The vibration level observed in the study staircase evidence a clear need of an intervention to increase its serviceability and consequently the user's comfort. Before demonstrating the experimental results, it is important to mention that the staircase stringers are supported on each floor by beams, and the connection between the beams and the stringers is made by means of an 8mm metal plate and a 20 by 100mm screw. And why this is important? This is important because due to this solution, rotational movement is possible. So the behavior of the two upper flight of steps is independent of the behavior of the two lower flight of steps. which means that they can both be treated as individual parts. This was verified during the experimental measurement. This observation is important, and now it's important, and now we can describe the experimental results. The fundamental frequency measured was equal to 13.9 Hz, and the damping estimated applying the half-power bandwidth method was approximately 1.18%. The fundamental frequency is under the cutoff frequency of 16 Hz, so, and therefore, it's possible to obtain a resonance response when ascending and descending the staircase with a step frequency of approximately 3.5 Hz, which is the fourth submultiple of the staircase fundamental frequency. Now, since it's possible with this step frequency to obtain a resonance response, all walking tests were made with this step frequency. The maximum vibration occurred for descents, reaching peak oscillations of approximately 2 and 5.4 meters per second squared for a single pedestrian and a group of pedestrians, respectively. Before proposing any improvement measure, the FEA model initially created needed to be calibrated, so the numerical accelerations were close to those to the experimental accelerations. Only after this, the improving measures could be proposed and be valid. An FA model of the study steel staircase was created using the analysis software SAP 2000, and the accelerations were obtained applying footfall first time histories. Another three methods are described in the paper, but this was the most accurate method. As you can see, it's important to mention that, as you can see, only the two upper flight of steps were modeled, since their behavior is independent of the two lower flight of steps, as explained before. The natural frequencies and shapes of the vibration modes numerical obtained were close to those experimentally measured, as you can see from the table. The maximum accelerations and these maximum peak accelerations were obtained for the same step frequency of 3.5 Hz were calculated, and for a single pedestrian and a group of pedestrians were approximately equal to 2.1 meters per second squared and 6.6 meters per second squared, respectively. This means that the initial model is calibrated, since both numerical accelerations and experimental accelerations are close. Here are described the different improvement measures proposed, and I just want to emphasize that the improvement measures aim to be employed in practice for increasing the serviceability of the actual staircase. It's not intended by any means to alter or demolish the existing structure. So, improvement measure number 1 was weld or screw an additional stringer in the longitudinal direction between the two existing stringers. It was verified that it was only with the HSS cross section of 250 by 100 millimeters that was possible to decrease the accelerations by values under the acceptable limits. Initially, we tried with a cross section with the same height of the existing stringers of the actual staircase, but it was not possible to decrease the accelerations. Improvement measure number 2: connect a steel cable between the HAB 180 beam. Was the beams in the this is the beams are the beams in the floor area, and it was intended to connect these beams to the intermediate lining. Unfortunately, this was one of the worst improvement measures. The acceleration did not decrease as we expected. It was intended to reduce the flight of steps deflection and therefore the accelerations, but it was an effective measure. The improvement measure number 3 consisted of in the placement of 2 additional beams at the flight of steps mid-spans in the transverse direction supported by an added column. The beams employed in this measure consisted of a steel hollow structural section 150 by 100 millimeters. This cross section was the one that gave rise to the lowest accelerations. From this cross section, acceleration ceased to decrease. The employed column must consist of a European wide flange beam HAB 180 or HAB 160. It's not being possible higher cross sections because the reduced space between the flight of steps. But the most important here are the beams placed in the transverse direction. So this is not the most important. Add the improvement measure number 4. It was at an intermediate column in the landing area simulated by a fixed support. This measure consisted of adding a column on the intermediate landing in order to reduce the length of the staircase span, thus decreasing the vibrations. The fourth proposed measure did not nearly affect the first vibration mode, which also caused the acceleration to not substantially reduce. This was also one of the most ineffective measures. The improvement measure number 5 was duplicate the height of the sample staircase stringers. HSS steel stringers with a cross section of 120 by 60 mm were added to the initial FEA model, placed under the existing stringers supporting the flight of steps. This reinforcement measure is important since it implies that the sample staircase should have been initially designed with HSS stringers about twice the height to avoid excessive vibrations. And finally, the improvement measure number 6. As it was described before, the flight of steps is supported on a HAB 180 beam with the connection between both elements allowing rotation to occur. So it is suggested as an improvement measure to transform the current pin support referring to the connection into a fixed support. For example, welding or screwing the stringers directly into the HAB 180 beam, which is the beams in the floor area, which are the beams in the floor area. This will allow the rotational stiffness to increase and consequently decreasing the vibrations. And these are all the improvement measures proposed being concluded, and now we go to the next section. The accelerations obtained after employing these 6 improvement measures were compared with the acceptable limits proposed by the SCI design guide. Since this is the only design guide that directly refers to an acceptance criteria for staircases. As we seen before, improvement measure number 2 and number 4 were the most ineffective measures. Improvement measure number 6, it was it is also an effective measure, but it was possible to decrease for approximately half of the initially obtained. With the improvement measure number 1, 3, and 4, 5, it was possible for single pedestrians to obtain accelerations under the acceptable limits. These were the more effective measures. With the improvement measure number 3 and number 5 for a group of pedestrians, it was not possible to decrease for values under the limits, but taking into account the accelerations initially measured, these were effective measures even for a group of pedestrians. To conclude, the accelerations measured in the study staircase were significantly high, reaching values of approximately 2 and 5.4 meters per second squared. Aiming to reduce the acceleration, 6 improvement measures were proposed. Improvement measures 1, 3, and 5 were found to be the most effective. This measure reduced the acceleration and increased the fundamental frequencies, placing it off the range of submultiples excitable by the pedestrian step frequencies. The improvement measure number 5 is of particular relevance since it demonstrates that the staircase stringer should have been initially designed with a HSS cross-section twice the height in order to verify the serviceability limit state. Finally, future staircase design should be performed considering the dynamic behavior and employing different numerical methods to predict human-induced vibrations, thus avoiding pedestrians on safety concerns and after construction modification with additionally unwanted high costs. Thank you, and I'm hoping to hear from you.